In this lesson, we're going to look at solid objects now. And in physics, we call solid objects continuous mass distributions. So that is just solids. And just to remind ourselves of the center of mass calculations for the point particles, we took the center of mass of a system of point particles based on m1, x1 plus m2, x2 through all the other mass and positions that are part of the system divided by the total mass, and we get our center of mass, those weighted position vectors. Well, we have an identical calculation, just a little different notation using the summation operator sigma, where we're replacing the m1, m2 by the total mass. Now, the reason I bring this up is that we're going to use this same concept, but now update it into the calculus world. So the first example we're going to look at is just for a one-dimensional solid object. So even though it's drawn and it looks like it's a thick bar, we have to think of this mass as really just being only along the x-axis. So it would be too tough to draw if I just drew it like that, so I made it the thicker bar. Now, we have to introduce the mass particles when we do the calculus version, or the continuous mass or solids calculation. So the first thing you want to do is introduce the calculus version of a point particle. And the calculus version of a point particle is this dm. So we always want to put a dm slice into the problem and think of it as really just, as I've said, a calculus point particle. And then x becomes the variable from the origin to that dm spot. So here we're saying this is a bar that goes from 0 to the full length of the bar, L. And then dx is the differential space that dm sits on. And just to note that in calculus, those dm's are referred to as differential masses, and they're infinitesimally small so that we have an infinite number of them. So now we have a problem with brute forcing a calculation. So this is where calculus comes in. Ideally, if we were going to just keep doing what we were doing with our discrete point particles, we would be doing this calculation here. We would be literally summing up all of these differential point particle m1, x1, but we can't do it because we have an infinite number of them. So that's a problem. And this is just showing that they're infinitesimally small. That's in the limit as dm goes to 0. Now, the calculus version of that summation is integration, and I'm not going to go through why that works in calculus, but that's our integration of, I just flip-flop the x and the dm, but integral x dm. The integral is the summation of all those dm's. So as far as our problem solving is concerned, we're going to be using polynomial functions if we're given functions, and I have some examples that we're going to look at. But this is the most important equation. Let me erase some of my additional here, because this is the one you want to box and remember as the equation for all of the calculus continuous mass distribution problem solving that we're going to do. And as an example, let's take a look at how we apply this. All right, so we're going to basically look at the same problem we just talked about. But before we do that, let me just make a note to you that there are really only two versions of this one-dimensional rod problem that we're looking at. The first one is the one we're going to now look at. We're going to assume it's a uniform density, so the kilograms per meter along the rod doesn't change. So that linear density is given by the Greek letter lambda, so you can put lambda in there. Lambda. And that is density. It's one-dimensional, mass per length. And that's constant. So for our bar, that will equal, and we'll do this down below, but I'll put it here as well, the total mass divided by the total length, and that remains constant in the problem we're going to do. Now for homework, you are also going to do one. That's on the next page of notes, and you'll do that for homework, and then we'll go over it in class, where lambda is now given as a function. So it's getting kind of heavier as you go off to the right. And if, in this case, it could be any function, but if the density is given by beta times x, where beta is a constant, but lambda, the overall units with beta nx, still equals kilograms per meter. We'll talk about how you're going to problem solve with that. But first, let's just do our constant density calculation and see how this kind of works out really nicely. I guess the other thing to note is we don't really need to do the calculation to know where the center of mass is. For a bar of length L, if it's uniform, it's going to be right in the center. So we know the center of mass is at L on 2 before we even start, and we would just use symmetry and nature's balance point to say the center of mass is going to be here, unless we were told we have to use calculus to show this. So, and that's what we're going to do here, use a little bit of calculus. So regardless of whether we're using the uniform or the non-uniform, you are going to start here. So this is the first thing you will always write down when solving any of these types of problems. The second thing you are going to want to do is to think about the limits. You need to sum up all of those dm's. So you are going to put the limits of integration in based on your summing from 0 out to L. The second, well, I can say that's the second. So if that's the first thing, let's put this as the second. Then the third thing you want to do, and you will always be doing this, always replace the dm with a dx using lambda. So dm over dx, remember we said in the last page, we said dx is the differential spatial extent of dm. dm divided by dx will always equal lambda, regardless of whether it's constant or not. So for your homework, you're actually going to plug in beta x for lambda, and then you're going to bring the dx up like we did here. So in our example, we just take the dm and we substitute it in here, and we are ready to go. You can see here it all kind of falls into place. The m's cancel, constants come out of the integral, so the 1 on m comes out. The m on the top here cancels with that m. The L is a constant, it comes out, so that's why the L is here. We're left with the integral, x dx, integrate increase, x squared on 2. When I evaluate it, final minus initial, I get some more nice cancellation. L cancels with L squared, and voila, we could have used calculus and not relied on nature's balance point or a conceptual understanding to calculate our answer. So again, you're going to do the part B for homework for me on the next page. The only difference is you are going to substitute in the non-uniform lambda, beta lambda. You'll leave beta in there as a constant, and you'll calculate your answer, and I have the answer shown for you, and we will go over the solution together in class.